Hi everyone, my name is Chris Coey, and today I'll be talking about Pajarito's MathOptInterface Makeover. So suppose K is a proper cone, meaning it's convex, closed, solid, and pointed. Now we define a general form for mixed integer conic problems as follows. We have a variable x, a linear objective, some linear constraints, and some conic constraints, and then finally integrality constraints on a subset of the variables. In practice, the cone K is going to be a Cartesian product of recognized cones. And note that this problem is convex when those integrality constraints get relaxed. Now, it's quite a general form because any mixed integer convex problem can be homogenized into mixed integer conic form. And the reason we might want to do that is because conic duality enables us to design powerful algorithms for mixed integer convex problems. So let's talk about these algorithms. So first of all, recognize that MILP solvers use advanced cutting plane techniques, and they use LP simplex solvers to rapidly reoptimize after cuts are added. So outer approximation methods take advantage of this. They use polyhedral relaxations of the convex constraints. And if these relaxations are tight, then we rarely need to solve the convex nonlinear subproblems, which typically don't benefit so much from warm starting like LP does. We're talking about a conic outer approximation method here. And the reason is, well, first of all, conic solvers can handle non-smoothness. And oftentimes, strong mixed integer convex formulations are conic anyway. So we can define the cone K in terms of its dual cone as follows. And because of this representation, we can write our conic constraint in an equivalent semi-infinite linear form like this. So any finite subset of these z points from the dual cone K star gives us a polyhedral relaxation through these linear constraints here. So we present the first conic duality-based branch and bound outer approximation algorithm in our paper from 2020. And this algorithm uses these K-star cuts from dual solutions or rays to continuous conic subproblems. And if no strong duality failures are encountered, then it's going to detect infeasibility, unboundedness, or return an optimal solution in finite time. So the first algorithm is this iterative algorithm here, and this alternates between solving this mixed integer linear outer approximation model and a continuous conic subproblem with a primal dual conic solver. But I'm going to skip that one and move on to our OA solver-driven or single tree algorithm. So in this algorithm, the OA solver, the mixed integer solver, is going to manage the search tree. So at the top here, we start by solving a continuous relaxation using our conic solver. Obviously, if that's infeasible, then our mixed integer conic problem is infeasible. Otherwise, we're going to add some initial K-star cuts, which give us a sort of fixed polyhedral outer approximation of our problem, as well as these relaxation K-star cuts obtained from the dual solution to that relaxation. Then we call the branch and cut OA solver. And in a lazy callback down the bottom, if we get an integral solution, then first we check whether the integer part of that solution has repeated. If it's new, then on the bottom left here, we're going to solve a conic subproblem using our conic solver. And in that subproblem, we fix the integer variables to the values in that solution we get in the lazy callback. Now, if that's feasible, then we get a primal solution and we store that, and later we may pass it back to the solver through a heuristic callback. And whether or not it's feasible, we're going to add these certificate K-star cuts from the dual solution or ray to that subproblem. Now, if instead that integer solution had repeated, then we can't solve a new subproblem because we've already solved it before. So we just check whether that solution is feasible for the conic constraints. And if not, then we're going to add some separation K-star cuts, which don't require solving a subproblem, but they do cut off that point. So Pajarito version 0.8, released on 21st of June, is a complete redesign and rewrite of Pajarito. So most importantly, we've dropped support for MathOptInterface and added support for MathOptInterface. So here we can see the architecture of Pajarito. So if we have a mixed integer conic model in JUMP or convex.jl, Pajarito will take that through MathOptInterface, and then it will call out to the optional continuous conic solver and the optional mixed integer outer approximation solver. In fact, we use JUMP to manage these conic and outer approximation models and solvers. So in addition to supporting MOI, the new version of Pajarito also has some new algorithmic features. For example, limited support for special ordered set type constraints. So because we're calling out to both conic and MIP solvers, the formulation choice is going to impact both of these solvers. So consider first just the continuous conic solver. And taking Hypatia as an example, what we've found in our work with Hypatia is that natural formulations tend to solve faster than equivalent extended formulations, which are more complex and have higher dimensions. And this makes sort of intuitive sense. Now, considering the MIP solver for outer approximation, obviously the dimension of the variables and the sparsity of the cuts and the numerics of the cuts are going to matter. The complicating factor here is that some extended formulations actually accelerate outer approximation by tightening polyhedral relaxations. We'll come back to this point at the end of the presentation. Fortunately, though, JUMP makes it easy to compare different formulations because they're very easy to model. And just to enable more different choices of formulations, in the new version of Pajarito, we have added a generic cone interface like that of Hypatia. So in this cones module, we can define a convex cone K, and that convex cone is associated with a struct in the module. And we're going to define several K-star cut oracles for the cone. So first of all, the initial cuts, which builds up a fixed initial polyhedral relaxation of the cone. The subproblem cuts oracle is given a K-star cut from a dual solution array of the continuous subproblem. And then it's going to add one or more cuts that are at least as strong as that cut. Typically, these cuts are extreme rays of the dual cone. And then the separation cuts oracle takes a point S and checks whether S is feasible for the cone. And if it is significantly infeasible, then it's going to add cuts that separate S. And then for an extended formulation that's going to be internally managed, there are some additional oracles that need to be defined. And again, we'll return to that at the end of the presentation. So currently in Pajarito itself, we've predefined the second order cone and the PSD matrix cone, as well as the two standard three-dimensional non-symmetric exponential and power cones. And in our experimental extension package, PajaritoExtras, we've added support for around a dozen cones that are recognized by Hypatia. And we can sort of slot these into three different classes. First of all, the PSD slice cones, which are intersections of slices of PSD cones and the dual cones of these cones. The spectral norm cones, which we won't discuss more in this presentation, and the spectral function cones. And using these cones in the package PajaritoExtras, we've formulated many different mixed integer conic examples. So let's look at the example of the PSD slice cones. So we can characterize these cones as follows. Here, lambda sub L is a linear operator from the vectors to the symmetric matrices. And we can see that these lambda sub L's of S are constrained to be positive semi-definite in that definition. So for example, we have the PSD cone itself or sparse PSD cone, or the dual polynomial sum of squares cones. Now consider a constraint S in K. So for initial cuts, we can simply impose, for example, that the diagonal of each lambda sub L is non-negative. And to separate a point S bar, we can compute the eigendecomposition of lambda sub L of S bar. And then for each negative eigenvalue, we can add a simple separation cut. Now let's consider the more difficult case of the dual PSD slice cones. So if we define lambda star as the adjoint of lambda, so lambda star is going to take us from the symmetric matrices to the vectors, then K star can be written as follows. You can see there are these auxiliary variables inherent in that definition and an equality constraint. So an extended formulation for K star in general requires auxiliary variables. And this is the case, for example, for the dual sparse PSD cones, which are the cones of PSD completable matrices, and the primal sum of squares cones. So suppose that K is a dual sum of squares cone parameterized by these collection of matrices P sub L. Then we can write the lambda sub L as follows, and its adjoint on the right there. So it has a fairly simple form. Then for the primal sum of squares cone K star, we have a good set of initial cuts, simply S non-negative. And that we can see from the definition of lambda star there. However, we don't have a good analytic procedure for checking feasibility of a point and obtaining separation cuts for the primal sum of squares cone. So what can we do here? So in Pajarito now, there's this feature that allows optimization-based separation. So let S bar be a point and C be the cone that we need to check feasibility for. We can solve this primal dual conic problem where the primal is simply the feasibility problem. And the primal has an optimal solution, of course, if and only if S bar is feasible. But if it's infeasible, then the dual has an improving ray Z that satisfies this condition S bar prime Z less than 0. So clearly, Z provides a separation K star cut in this case. Fortunately, problems like this can be solved very efficiently and reliably with Hypatia. In fact, all we need to do is load this problem once at the start, and then every time we need to solve it, we just modify the S bar vector in Hypatia without having to allocate new memory. I'm going to illustrate with a fun little example. So I call this problem the polynomial facility location example. So let's say we have non-negative polynomial flows over continuous time from t equals 0 to t equal 1. And we have facility I with a fixed cost of opening f sub I. It has a maximum output rate, and we open it if a binary variable x sub I equals 1. Now, customer J is going to have this demand rate d sub j, and the cost per unit of flow from facility I to customer J is C. Now, we work with degree D polynomial variables, y sub ij, which is a univariate polynomial in the time. And that is the flow rate from I to j over the time t in 0 to 1. And of course, we minimize the total cost, satisfying the capacities and demands. So if we model this as a high-level mixed integer polynomial problem, we might have the following. So we're going to minimize those fixed costs plus the costs of flows. And you can see there is this integral term in the objective. And then we have these linear constraints that are semi-infinite because they are for all t in 0 to 1. Now, using polynomial sum of squares modeling, we are going to exactly reformulate this problem as a mixed integer conic problem over primal sum of squares cones. So to do that, we reinterpret those yij polynomial variables in an interpolant basis and use exact polynomial quadrature to write it as follows. And here, KSOS. of P is a primal polynomial sum of squares cone. And that parameter P is that collection of matrices, which is dependent on the interpolant basis and these domain constraints, T in 0 to 1. Now we can solve this problem with Pajarito using the extension package PajaritoExtras, which supports mixed integer sum of squares problems. So we run some experiments using polynomials of degree 6 and varying the number of facilities and taking the number of customers, m equals 2n. And what we're going to compare here is the performance of Pajarito using the natural formulation over the sum of squares cones directly against the extended formulation, which uses PSD cones, and obviously lots of extended auxiliary variables. So as we go down the rows here, we're increasing that number of facilities and customers. And the NF here, it means the natural formulation. The EF is that mixed integer semi-definite problem. We can see that Pajarito does, quite reliably well with the natural formulation, converging in a small number of iterations. Whereas the extended formulation suffers from numerical issues. It's hitting these errors. It's also much slower. And that is because both the outer approximation MIP solver and the conic solver are both struggling to deal with the size of the extended formulation. So this example and several other mixed integer polynomial examples that we have in PajaritoExtras point to the idea that potentially using natural formulations in Pajarito can be quite beneficial. Okay, so now let's look at a different class of cones. Specifically, we'll look at the vector spectral function cones, an example of which is the geometric mean cone, which is the hypergraph of the geomean function. So we can write an extended formulation for a geomean cone constraint in terms of some auxiliary variables, linear inequalities, and 3D exponential cone constraints. Now, if we use the extended formulation in the outer approximation model, we can get tighter polyhedral relaxations. To understand this intuitively, think of the Fourier-Motzkin algorithm, in which a polynomial number of cuts in the extended space can project down to an exponential number of cuts in the natural formulation space. So you could think of the L1 ball LP extended formulation, for example. Now, the complication here is that what we found in our experiments with Hypatia is that Hypatia can solve the natural formulations faster than the extended formulations, typically. So we want to use the NF for the conic subproblems with Hypatia, but the extended formulation in the outer approximation model. And the solution that allows us to do this is to extend cuts and primal solutions from the NF space to the EF space. So let's try and visualize this sort of strength argument here. So take a simple geomean ball constraint, geomean of W is greater than or equal to 1, where W is in 3 dimensions and it's constrained to a box. Now, suppose we have 7 K-star cuts in the natural formulation space. We're going to project down onto just W1 and W2 so that we can visualize this. So on the left here, the black dotted line is the boundary of the convex geomean constraint. And the red region is the polyhedral relaxation of that when we just use the NF. And that's given by those 7 NF K-star cuts. But if we use the extended formulation, we get this much tighter polyhedral relaxation in blue. And on the right here, we're just showing for each of the 3D exponential cone constraints what those NF K-star cuts, what they are extended to. So clearly, the extended formulation allows us to get tighter polyhedral relaxations here. Let's look at a simple simple example problem. So we're going to be selecting the number of units of each item, and these items have weights and values. So given some weight budget, we want to maximize the geomean of the values. So our problem looks like this, and this can be reformulated as a mixed integer conic problem with a geometric mean cone constraint. So just to start with, we're going to run a separation-only algorithm in Pajarito on the continuous relaxation. So we're dropping those integrality constraints, and we're not going to use Hypatia. We're just going to separate infeasible points. So on the x-axis here, we have the number of items. And then on the left, we have the number of iterations needed for this separation-only algorithm. So we can see that when using the EF, which is the black line, we need much fewer iterations to converge. And when I say converge here, I mean to get a solution that is epsilon feasible. Now, on the right, we can see that the solve time also is dramatically better. This is the overall solve time, counting all of the iterations. Now let's reimpose integrality and use the standard Pajarito algorithm that calls Hypatia as the conic subproblem solver. So we're varying n again as we go down the rows. And then on the left part, we have the using the extended formulation in Pajarito. And we can see, interestingly, that the number of iterations doesn't increase that much as n increases, and we can generally solve all of those problems. But if we don't use the extended formulation, if we go over to the right set of columns, just using the natural formulation for both the conic subproblems and the outer approximation model, the iteration count and the solve time very rapidly blows up, and the problem becomes intractable for Pajarito. So this, of course, is a familiar story. So it generalizes the approach that the old Pajarito uses for the second order cone, and that many commercial mixed integer second order cone programming solvers use. So in order to allow Pajarito to internally manage these extended formulations, we have to add a couple of extra oracles for cones that we're going to use the EFs for. So first of all, we need an auxiliary variables oracle that helps us set up the OA model with the extra variables and linear constraints. And we need a primal solution extender oracle that takes a NF space primal solution from the conic solver and extends it into a warm start or a heuristic solution for the MIP OA solver. And then furthermore, those three K-star cut oracles that I mentioned earlier in the presentation, the initial cuts, the subproblem cuts, and the separation cuts, those oracles need to be modified to extend those cuts. And usually there's a way to do that that's highly refactored. So it ends up being not very complicated to code. Now, what we've observed in our computations is that an extended formulation is often worthwhile to use if you only need sort of a small number of low dimensional cones to represent the same constraint. But for extended formulations that involve PSD cones, these are often too large, and we've encountered numerical issues, and they don't have strength benefits that are as clear. So for example, we saw the geomean cone, which is a vector domain, and that has a nice, simple extended formulation. But the matrix domain analogy of that is the root determinant cone. And for that extended formulation, which involves high dimensional PSD constraint and exponential cone constraints, the benefits are not so clear. And we run into numerical issues and slower solve times. Now, all of this functionality could probably be sort of rewritten using MOI bridges. This would, I think, come at the expense of readability, and it would be a bit harder to sort of experiment with it. but it's something we could consider down the track. So thank you for listening. And let me just finish with some references here.